So please, Martin.
Thanks. Okay, can you hear me? Also those at the back? Okay, so first of all, great thanks to Georges for organizing this meeting here. It's really a great place. I just love to be here, and thanks a lot for the invitation. So it's really a...
No, it is switched on the icon. But it works.
Okay, so better? Okay, good. So once again, it's Georges' fault, of course, that it didn't work, but nevertheless, thanks to Georges for organizing this, for doing this conference. It's really great to be back. So what I would like to tell you about today is a fairly simple problem. This is joint work with my ex-PhD student and one of his colleagues, and it is about something I've been doing for a long time. So it's about mean variance problems, but there's a small twist. So the problem I'll be looking at is very classical. So you have a standard model. S is your price process. Then you use trading strategies. You look at the total gains from trading. And then basically I want to do two kinds of problems. One is where I say, okay, I'm given a payoff, and I want to approximate this in an L2 sense by choosing an initial wealth and a strategy. And then maybe I can use the best initial wealth here as some kind of approximate pricing. So this is what I call the mean variance hedging problem. Alternatively, I can also look at the corresponding portfolio selection problem. So there, I would like to choose a strategy, trading strategy theta, which maximizes the difference expectation minus some multiple of the variance. And the alpha, the coefficient here, is something like the risk aversion or the variance aversion I have. So this, in principle, is a standard problem. Everything is defined in the usual way on a filtered probability space. But there's one small twist. My S is adapted to the filtration F, but the strategies I'm allowed to use, they have to be predictable for a smaller filtration. So I have my prices which are observable in a big filtration, but I'm only allowed to use for trading a smaller set of information. And then the question is, what can one do here? So first thing we did, we looked at earlier work, and basically there are two types of cases. If your filtration that you're allowed to use allows you to see the underlying prices, this is fairly easy. Because then basically what you do is you take your payoff, you project it down on the final observation, then you have a problem directly in the smaller filtration, and you just solve the problem there. So this is for mean variance hedging, for the portfolio selection problem. You can do similar tricks. So if you can observe in your hedging filtration prices, then things are easy. And if you then look at the situation where what you can use for trading does not contain the observation of prices, then essentially there's really not much work. So there is a very old paper going back to ideas from Gianni Di Masi, Wolfgang Runkel, Eckhard Platen, which looked at this case when your underlying is a martingale, and then things are easy because then you can do just projection arguments. But for semi-martingales, the interesting case, especially if you think of mean variance portfolio selection, there you don't want to do this with martingales because then you just don't trade. Then there is just a couple of papers by Misha Manya and co-authors, and the assumptions they have there already exclude, for example, the Black-Scholes model. So it's really restrictive. Now, Mario Šikić, one of the co-authors, in his PhD thesis looked at one very specific case. So he looked at the discrete time model where you had prices which are additively or multiplicatively of an independent structure, and the filtration you're allowed to use is delay by a certain number of time steps. There he could do very explicit computations and some asymptotics and find some results for the portfolio selection problem. But otherwise, we looked around and basically there's nothing. So what I'll tell you today is I look at the case where I have very strong assumptions both on the filtration and on the price processes. So the filtration is just the simplest one. This is one that Jim Gatherell probably would like. This is the zero information filtration. I just don't see anything, so all my strategies are just functions of time. And I mean, this is not completely irrelevant if you look, for example, at optimal liquidation problems. Many optimal liquidation problems are being solved exactly in this class of strategies because people don't know how to do it more generally. Okay, so this is one assumption we make. So I'm allowed to vary my trading over time, but I do not get any other information. And the structure I impose on the price process is something like this. So this is like something affine. So basically, I start with a martingale, so this is my y, and then S is a kind of affine transformation of this form, some function multiplied by the martingale plus another function, finite variation, something like this. Looks quite special, but it includes, for example, arithmetic Lévy models, it includes exponential Lévy models. The only thing you need is a little bit of integrability, of course, so you get something square integrable. It includes the Bachelier model, it includes the Black-Scholes model, you can also use an Ornstein-Uhlenbeck model. So it is a fairly large class of processes that is included in here, and with this combination, so this kind of affine type structure for prices plus zero information, we actually find fairly explicit solutions. So how does that work? Okay, so I need a number of notations which will appear later on. So here is the structure of my affine type process S. And of course, I can view this as a semi-martingale and look at its decomposition into the martingale part and the finite variation part. And of course, the martingale part, if you do the calculations, is simply the integral of g with respect to y. And then what we need for assumptions is well, basically we need, so these are all kinds of dual predictable projections. So we need the quadratic variation of the martingale part, and of that the expectation. And we need something involving the other parameters and something involving the drift. This is the precise class of integrands we are looking at. I just put this here for completeness. So main point is you have the basic ingredients f and g here, and in terms of those, we express the conditions and the strategies we want to use. The assumptions we impose are two. So there is one condition which says the function g is bounded away from 0. So what's the function g? So the function g is the factor in front of your martingale component, or if you look at the martingale part of your price process, it's the integrand here, and saying that this has to remain bounded away from 0 is like saying volatility never vanishes. Otherwise, you get trouble. And the other condition is something like this. If you compare the drift part of your decomposition with the martingale part, then this should not be too large in a certain sense. So if you have too much drift compared to volatility, you also get problems. So this is this kind of condition we need. And if we have this condition already, we can rewrite the second one And it's not really important what it looks like. The point I want to make here really is the ingredients of our model are the functions f and g and the martingale y, and the condition then is expressed completely in terms of the model primitives. Okay. So these are the assumptions. So the one assumption is the function g is positive, the other is something relating drift and volatility. With the first condition, positive volatility, we have a more technical result, but this underlies what we're doing. And this says that what we really need to look at is stochastic integrals of the underlying price process, and these can be rewritten as sums of a constant and the stochastic integral of the martingale part. It's not terribly surprising if you look at this, because basically S looks like this. So you integrate, if you integrate some deterministic theta with respect to S, and you do integration by parts and multiply things out, this is deterministic, and this basically, when you do the calculus, you find a constant which looks like this, and you also find explicitly the strategy appearing here, and this, so basically we have an input strategy, we have an output integrand, and the output integrand is given in explicit form by this linear transformation. This does not look very exciting. What is useful about this is really two things. One thing is we originally need to look at a stochastic integral of a semi-martingale, and for handling L2 things, this is annoying because you have the drift part. But you can reduce this to something else involving only the martingale part, and that's much easier to handle. And the second thing is the transformation of the integrand is explicitly given, and this is really tractable because we will see that this transformation from the S integrand into the martingale part integrand, this has good properties. So that's the second main result. If we have both the minimum volatility assumption and this ratio drift volatility condition, then the operator A appearing here is not only a linear operator from the space of our integrands to itself, which is also invertible always, it also has the very nice property that it is continuous, and the inverse is continuous as well. And this allows us to see fairly easily that the space of all our stochastic integrals is a closed subspace of L2. Why is this useful? Well, this tells us that our problems actually have solutions. So this is an existence result, which is nice to have, but it doesn't give the solution yet, of course. But at least under very basic assumptions, we know we can always solve the hedging problem, and there's always an optimal strategy for the portfolio selection problem.
What's the interpretation of the complementary? Is there an interpretation?
Sorry?
Is there an interpretation of the complement of the? It's a closed, so you have a complement there, or is there?
We didn't think about this
Okay.
actually.
I don't know. It's
I
just
don't
curious.
really know. No.
Okay.
I'd have to look at this. Good point. So the question was, what's the complement of this subspace here? And I don't really know. I mean, it should be something like a kind of densities of martingale measures, but only sort of martingale measures which make sort of like this which make like a projected version of the price process onto the deterministic filtration, which make that into martingale. It has to be something like this.
Probably the unhedgeable part.
Yeah.
If you project on the hedging.
I mean, okay, so if you fix your H, So if this is your payoff, then the projection on that is what you can hedge, and of course the rest is what you would call the unhedgeable part. But if you then ask, okay, but what is the space of unhedgeable parts like? That's, I think, is what Georgie was asking, and this I'd have to look at more carefully. So this I cannot answer directly. It might be that one can express this in terms of the inputs, but I really don't know because we didn't look at that. We were actually just looking for the solutions here. Okay, so what does the solution look like? Well, of course, we assume our two conditions, minimum volatility and ratio drift volatility controlled. And then for the hedging problem, what we do is very classical. We take the big filtration, we project our payoff onto the martingale part with an orthogonal martingale part. This then gives us an integrand in the big filtration, which of course we cannot use, and then we project that integrand down onto the smaller filtration, okay? Which will give us a deterministic function, and then explicitly in those terms, the optimal pair looks like this. So the optimal strategy is just the inverse of this operator applied to that projection here. So explicitly here is the expression in terms of the parameters and the projected integrand here, and the optimal initial capital looks like this. And so what this means is to solve the hedging problem in this filtration, you need basically two things. You just need standard martingale techniques. Just project your random variables in the usual way in the big filtration of your martingale, project the integrand down to the smaller filtration, and then you have an explicit expression. Okay? And the portfolio selection problem, the mean variance optimal investment, this looks like this. So you again have an explicit formula involving the ingredients of the model. So I don't really want to explain or write out in complete detail what it looks like. Main point is you know exactly what the strategy looks like, the optimal investment in this mean variance sense in terms of the parameter of your model and in terms of this explicitly given operator here. So once you have a specific model of interest, this will give you explicit formulas. I'm not writing out the explicit formulas, but we did look at some examples. So examples, as I told you, arithmetic and exponential Lévy processes satisfy all the conditions. Then we can also do explicit computations of the strategies. So in terms of the Lévy triplet, we can give you explicitly the optimal investment and also for a given payoff, once you have projected it, the optimal hedging strategy. And what one can also do, as I suggested at the beginning, you can say, okay, take a payoff and look at the optimal hedging pair, optimal initial capital, optimal strategy in this L2 sense, and look at this optimal initial capital as a kind of option price based on quadratic hedging. What does it look like? And we did some computations for that, for both the Bachelier and the Black-Scholes model, for the special case where H is a European coal. So what does this mean? So what we compared, and here are the results, so here are the parameters we used. So the full information price, this is the Black-Scholes model, is just the usual Black-Scholes price, where you do your Black-Scholes delta hedging. And then, of course, you replicate the payoff exactly. The zero information price is the following. We only use a function of time as our strategy. We use this in the Black-Scholes model, and then we approximate the call in the mean square error sense, and this is the initial wealth, which gives us the best approximation. And it's surprisingly really not that far off the full information price. We then said, okay, so of course here, with the full information price in the Black-Scholes model, you do perfect hedging. Here, this is not perfect hedging, so there's a hedging error. What does it look like? So this we could not compute explicitly. So what we did was we looked at the profit and loss and just did simulations of this. So we did the following. Here is the call payoff, and we subtract from that the optimal initial wealth and the gains from trade with the optimal deterministic strategy. And we did this for different strikes, and this is what it looks like. So it's reasonably concentrated around 0. It is a bit more to the left of 0. It looks not too bad, but of course there is. As you can see, there is a hedging error. We also looked at some strategies. So this is for the at-the-money call, the optimal strategy, which looks almost like a linear function compared to some typical hedging strategies in the Black-Scholes model, depending on the realization of the underlying. And we also looked at the quantiles of the optimal strategy. So these are the different quantiles from a number of simulations of the optimal strategy compared to the optimal deterministic strategy. So we did this for the Black-Scholes model. We also did it for the Bachelier model, which I'm not showing because I'm running out of time. So this basically is what I wanted to tell you. So thank you for your attention, and happy birthday, Bruno, and all the best wishes.